Okay, when we talk about planes, here's one thing to make sure we got here, because it's an important fact for several things we do today. AX plus BY plus CZ equals D. Okay, so that turns out, comes out to be a plane in 3 dimensions. The question though is, if I've got this equation in front of me, I didn't develop it, can I know anything about the plane? Specifically, what's the normal vector of that plane? And it's actually fairly easy. Remember, the normal vector is the vector that's perpendicular to the plane. Like I said, this is fairly easy to think about. So if I've got a normal vector, ABC, and I've got a point in the plane, x0, y0, z0, it turns out the equation is a times x minus x0 plus b times y minus y0 plus c times z minus z0 equals 0. Okay, so that's how we generate the equation of a tangent plane from a normal vector and a point. Well, like I said, my question over here is easy, because if you look at that, if I distribute the A here, distribute the B here, distribute the C here, then notice what the coefficient, I'm not going to do it all the way across, but all right, so that's just a number, right? That's just a number. So this AX, then I'll have BY and CZ. So you're with me here that if I've got this equation already, I know that the normal vector in, forgot my little symbol there, but the normal vector on here is going to be ABC, right? Because that's, I can get this into this form by just moving all those constant terms to the other side. So I would have AX plus BY plus CZ. And so that, anyway around it, the normal vector is ABC. Okay? So that's fairly nice. Go the other way with that. Now the other thing that we're going to use a couple of times here is how do we know if 2 planes are parallel? So I've got this plane and then another plane, say a little bit lower, but how can we for sure know if those planes are parallel? Well, again, it goes back to the normal vector, because this one I've got a normal vector to this one, call it N1, and then I've got a normal vector on this one, call it N2. Well, if the planes are going to be parallel, guess what the vectors have to be? The normal vectors. They would have to be parallel too, right? I mean, all the lines in here would have to be parallel, but the vector here would have to be parallel to the vector here. So if their normal vectors are parallel. And remember, how do you tell if vectors are parallel? Well, just one is a multiple of the other, vice versa. Right? That's what it means. Okay. All right, so with all that in mind, let's do this. Find the equation of the plane through 3, -6, 4 that is parallel to plane x minus 3y plus 2z equals 5. Find the equation of the plane through 3, -6, 4 that's parallel to x minus 3y plus 2z equals 5, okay? So, again, what we need for the equation of a plane, we need a point and its normal vector. Well, we just happen to have a point. So there's our point. And then we know that it's parallel to this other plane, which, what's the normal vector of that? Well, you can just read the ABC right off of that, right? So it's 1, -3, 2. So I want it parallel to that, so why not just make it the exact same? I mean, it's to be parallel, you have the vectors, or normal vectors are parallel. So why not just make it the exact same one? Just has to be a multiple of the other one. So there you go. So we've got, that's going to be our normal vector, that's going to be our point. So we've got A is 1 times x minus x0 minus 3, that's B, times y minus y0, which is -6, so it'll be plus 6. Plus the C, which is 2, times Z minus 4, which is Z0. Pretty easy. No problem. Now again, I think, I didn't check, but I think they'll probably want it in this, I don't know what you want to call it, just standard form or whatever. They'll get it to where the x, y, and z's are on one side and the constants on the other. I think that's how they'll usually want the answer, so just going to do that. So as I make it x minus 3y plus 2z, what do we got? Minus 21, 29, so it equals. So it's minus 29 on that side, so it'll be minus 29 on this. That sound all right? Does that look okay? That's what I had before. Yes? Is that okay? All right. Now, next. What we want to talk about next is, let's talk about distances between, we'll start with the distance between a line and a point. Talk about 3 dimensions. The distance between a line and a point, then we'll get into some other things eventually. Point in a plane, yeah, and other stuff. Okay, so, all right, so if I want to find in 3 dimensions, I want to find the shortest distance between a line and a point P that's not on that line. Line L, point P, which of course is not on the line. So I've got a line up here in space, the line, and then I've got a point not on that line. So how can I find that shortest distance between the two? So that, I mean, that line could be anywhere. The point doesn't necessarily have to be in the same plane, but for ease of drawing, I mean, it's well, I guess they, in some ways, are in the same plane, whatever the plane is. Let's just make it the surface of the board here. Okay. All right, well, so there, obviously what I need to find out is, you know, that distance between them is right here. The question is how we can do that. Well, in our three dimensions, a line, what we need is we need a vector for that line, and so we'll call that vector V, and it doesn't necessarily have to be associated with that point. Let's put it out over here. So vector V is just the vector direction of the line, okay? And then let's let, so let's let Q be that, because we don't know what this point is on the line. So we'll just let Q be that point, initial point of the vector there. And then we'll make this U vector from point Q to point P. Well, what that establishes then is a nice little right triangle. And let's call this angle theta here. And by trig relationship there, we would know that D, well, so we're, the two sides of note here are, by what I've established is I've got the U vector, the length of that U vector, and then V. So that, how's that related to that angle theta right there? Let's call it that theta. Well, that would be opposite over hypotenuse, right? So cosine of theta is the opposite, which is D, divided by hypotenuse, which is the magnitude of U. Well, so D is the shortest distance. That's what I'm trying to find. So if I solve that for D, I've got D equals what? Magnitude of U times cosine of theta. Okay. So if I knew that angle, could figure out that angle, I can figure out D. But is there an easier way to do it? Well, it turns out, yes. There's a much easier way instead of having to figure out that angle to doing this. For one thing, if I call this angle alpha here, alpha is good because alpha is the angle between vector V and vector U, and I know a little something about that. Well, oops, I put cosine, sine. Yes. I think I said sine, but I wrote it's my name. All right, sine. Because I was about to get in trouble here. What I was trying to do next. All right, it's sine because it's opposite. I know I said opposite over hypotenuse. I wrote cosine. My bad. One of those days. All right, it's sine. Sine theta equals D over magnitude of U, and so D is magnitude of U times sine theta. You guys are supposed to correct me on that. And so, checking it there. All right, but here's the thing. Alpha is the angle between the vectors, and that's going to be a little nicer for us here. Well, it turns out, notice that alpha is 180, or alpha is, let's do it, theta is 180 minus alpha, right? Because it's a straight angle. Well, yeah, if that's a relationship there by trig identity, well, I guess I should say that alpha is 180 minus theta. That's right, yeah. By trig identity, we know that the sine of theta is sine of 180 minus theta. That's a trig identity. Check that out. But the sine of the angle is the same as the sine of 180 minus theta, or pi minus theta, whatever you want to call it. Well, 180 minus alpha is 180 minus theta is alpha. So anyway, long story short, distance alpha. Turns out the sine of theta would be the same thing as sine of alpha. Well, this is helpful because, again, that angle is not going to be easy to come up with. However, if I multiply top and bottom here by the magnitude of v, which is, I'm just multiplying by 1 there, what I wind up with is magnitude of u times magnitude of v times sine of alpha, which is the sine of the angle between them, divided by magnitude of v. Which again is not particularly easy, but we learned a little something about u, magnitude of u times magnitude of v times sine of the alpha between the angle between them. That turns out to be the cross product magnitude, the magnitude of their cross product. So this right here is the magnitude of u, cross product, magnitude of v, magnitude. UV cross product, and take the magnitude of that. That's what that's what that calculation is. So all said, find the shortest distance between line L and point P. You can just do magnitude of this cross product of u, which is from a point on the line to point P. So u is a vector from P to a point on the line. Doesn't really matter. And of course V is the vector of the line. Those two things, if you do the cross product magnitude and then divide that by the magnitude of V, you get the distance between the line and point P. Okay, so this is the formula. Let's try. So find the distance between 3, 5, negative 1, and the line x equals 2 plus 3t, y equals 5t, and z equals 4 minus t. All right, so start with the easy one first. What is the vector of our line L, the V, what we call V over there? Well, because of the way these lines are constructed, aren't the coefficients of the t, we can use that for vector V here, 3, 5, negative 1, vector V. Easy enough. All right, now, for U, we've got point P, so we need a point Q on the line here. So, so this is point P. So what about point Q? Q is just a point on the line. Well, take your pick here. We can set t equal to 1 or t equal to 2, or how about t equals 0? Yeah, use t equals 0. Make it easier on itself, so it'd be 2, 0, 4. So U is just the vector, let's call it PQ. With our numbers there. So to get the vector from P to Q, we just subtract, right? 3, I guess it matters, 3 minus 2 is 1, 5 minus 0 is 5, negative 1 minus 4 is negative 5. I did that right. So now we get our distance. So the distance is the magnitude of u cross magnitude of v, cross v, vector v, divided by magnitude of v. So what do we got here? So our cross product of u and v. How do we get that cross product? Well, set them up. It's I, J, K. The I is the determinant here, so it's what have I got? Negative 25 plus 5. Then the J component would be the negative of 3, 1, negative 1, negative 5. Do I need to write that out? So the I part is this determinant. Then the J is 3, negative 1, 1, negative 5. And then the K plus K would be the 3, 5, 1, 5 determinant. That's what we're doing here. So what is that? Negative 15 plus 1. And then the K is 15 minus 5. So lever. Divide that by the magnitude of V, which V is that, so it'd be square root of 9 plus 25 plus 1. Just doing the squares, sum of the squares of all those. Now that's ultimately what we're going to do here too. So it's negative 20, what is that? Negative 14, so it'll be positive 14, positive 10. So what do we get for the top here? Square root of 400 plus 196 plus 100. Square those all up. Does that sound right? Divide by the square root of 35. So let's just call it square root of 696 divided by 35. I don't think that reduces. Not too bad, right? Just hardest part is that cross product. Any problem there, concern? Is that all right? Okay. Well, what about this? What about the distance between point P, which we'll call X, Y, Z, and the plane AX plus BY plus CZ equals D. I shouldn't use D there, but I'm talking about distance. I don't think we'll get too confused, hopefully. Okay, so here I got this point P up in space, X, Y, Z. And I've got this plane, wherever it is, down here. So I want that distance between that plane and that point, shortest distance? Well, not too hard to draw here. It would just be, I gotta come down here 90 degrees, right? Gotta set up a 90 degree. So let's call that point x, where it's that plane, x0, y0, z0, my plane there. Okay. Well, oh no, let's not do it that way. Sorry. That's the wrong drawing here. Try this again. Point P is x, y, z. And then we've got this x0, y0, z0 point. We're just going to make that any point in the plane. Okay, I don't want that to be necessarily that point down right below it. That's to the shortest distance. I just want it to be a point on the plane. Okay, so I don't have to mess with that specific point. Okay, and then we know we've got this normal vector for point P. But yeah, our shortest distance, like we said, is going to be, drop this down wherever it hits that plane at 90 degrees. All right. Okay, well, let's take that a look at this angle right, this triangle right here. That's going to be our right triangle of note. Now, what we can establish, yeah, is we can get this this angle, theta. Let's talk about that. And let's call this a vector u, because that's going to be the vector from that point in the plane, doesn't matter where, to that point x, y, z. That's our vector u, like we called it on our previous example there. So, this is our distance d we're after, right? Okay. So, in this case, we do have cosine theta involved, right? The cosine of theta would be d divided by the magnitude of u. Similar deal, we're solving for d, so d would be the magnitude of u times the cosine of theta, which, coming up with that angle would be difficult. However, let's note this. If I take, multiply top and bottom by the magnitude of n, which is this normal vector here, which would be parallel to the distance vector, if you will. Here's what I've got. Magnitude of n, u times magnitude of n times cosine of theta divided by the magnitude of n. Well, that just so happens to be the magnitude, or the dot product. The dot product is that, u dot n. Now, they'll throw in an absolute, dot product is just a scalar amount. And so they throw in the absolute values on that just to make it a positive. We want the distance to be a positive distance. Okay? So it turns out the distance between a point and plane, what you do is you take the dot product of u, which, remember, u is it's the vector between point P and a point on the plane, or in the plane. Doesn't matter which point in the plane you do. U is just the vector between the point P and any point in the plane. And then n is the normal vector of your plane. Okay. That's how you get the distance between a point and a plane. Shall we try one? All right, so find the distance between 113 and 3x plus 2y plus 6z equals 6. So there's our point P, there's our plane, which has a normal vector. Let's get that first. The normal vector is 3, 2, 6. Right? ABC. Well, the other thing we need then is vector is u. And so to get vector u, I need a point in the plane. Well, how are we going to get a point in the plane? Well, we just need an x, y, z. That works in that equation, right? That would be a point in that plane, an x, y, z. So how could we do that? Well, a good one looks like if I did x is 0, y is 0, and z is 1. Looks like a good one to me. You just have to come up with, I mean, worst comes to worst, just pick an x and a y, then solve for the z. In this case, I picked x and y to be zeros. But you can use whatever one you want. So that would make then vector u, well, vector u is the vector connecting those two, p and point in the plane. What would that be? 1 minus 0 is 1, 1 minus 0 is 1, 3 minus 1 is 2. So vector u would be 1, 1, 2. So we got our distance. The distance then is the absolute value of u dot n divided by magnitude of n. So what's the dot product here? It's these two. Numbers mixed up here. All right, so it'll be 3 plus 2 plus 12. 1 times 3, 2 times 1, 1 plus 12, which those are going to be positive anyway, so it didn't need the absolute values. What about the magnitude of n? Magnitude of n would just be the square root of the squares of those added together. 9 plus 4 plus 36. That's going to be 17 over the square root of 49. 17 over 7. Always come out that nicely. How's that sound? It's not too bad.